Hi everyone. In this video, I'll be demonstrating path analysis using Stata. And before I get started, I want to mention that underneath the video description, you can download a link to the Stata data file that I'll be working from in this example. So feel free to download that to follow along. You'll also find a link to a supplemental PowerPoint that I've put together that is going to go into a lot more detail concerning interpretation and so forth. So a lot of the emphasis in this video is going to be on the procedural aspects of running the analysis using Stata. And I'll be talking through various interpretations, but definitely the PowerPoint is going to offer a deeper dive when it comes to interpretation of the results. Now, in this presentation too, we're going to be focusing in on carrying out our analysis using the graphical user interface that's built into Stata. So basically, the SEM Builder is used to diagram or to create a diagram of your structural equation model. So in this case, we're going to be using it to create our path model that we're testing. So from that, we can actually carry out our analysis and be able to obtain our results. I do want to mention too that it's a good idea still, even though the graphical user interface is easier to use, it's a good idea to have to develop some understanding about how to perform the analysis using Stata syntax. And the reason why is that the syntax is oftentimes more efficient, particularly when you're working with larger models and so forth. So that's just kind of a suggestion I have as you are developing your skills in learning, in working with Stata for the purposes of SEM. So at any rate, we'll go ahead and just take a quick look at the model that we're going to be testing. This is it right here. You'll notice in this path diagram, this was actually drawn up using the graphical user interface in Stata. This example is based off a presentation by Whitaker and Schumacher in their 2022 book, A Beginner's Guide to Structural Equation Modeling. It's actually in the 5th edition right now. And this example is based off of data from McDonald and Cleland from 1984. Basically, this data is based off of responses to, I'm assuming, a survey from 173 non-union textile workers regarding their age, years working at a textile mill, deference to authority, support for labor activism, and sentiment towards unions, where basically higher values would reflect more favorable perceptions or sentiments towards unions. So as you're looking at this particular model right here, just kind of keep in mind how it's drawn up. In structural equation modeling, when you are creating a path diagram, the boxes or rectangles represent manifest or observed variables, and ovals or circles typically are used to designate latent variables. Basically, a manifest or observed variable is one where you have data on it, and then latent variables are typically variables that are kind of inferred from the pattern of associations among a set of manifest variables. So that's kind of a way to sort of think about it. Also in SEM, you'll see too that error terms are represented using circles. So in this diagram right here, you'll see that all of our variables are assumed to be manifest or observed variables. So we have age, years, deference, support, and sentiment. All of those are in rectangles, so we're going to treat these as manifest variables. And then the circles with the arrows pointing to those manifest variables, those are error terms, and basically they're reflecting prediction error in our current model. Now, as you're thinking too about the different types of variables, keep in mind that we don't typically use the terms independent and dependent variable or predictor and criterion variable in SEM like we might use in the context of multiple regression or perhaps analysis of variance. In terms of the terminology that's typically used is endogenous and exogenous variables. So as you're looking at the path diagram on your screen right here, just kind of take note that we have, again, these manifest variables, age, years, deference, support, and sentiment in rectangles, but we also have arrows that are pointing from one variable to another. So the single-headed arrow, like right here, from age to deference, that's based on an assumption that that age has some effect on deference. The path from deference to sentiment, that's a single-headed arrow pointing from deference to sentiment, that's reflecting the assumption that there's a potential causal effect of deference on sentiment. So all of the paths in the model right here, each of these paths are basically reflecting a proposal of a causal effect of one variable on another variable. Now, in terms of the variable designations, these variables right here, age and years, these variables don't have any arrows pointing to them, but we have arrows pointing away from them to other variables in the model. So these variables would be deemed as exogenous variables within our model. Now, any variable in the model that has arrows pointing to it from other variables are referred to as endogenous. Okay, so deference, support, and sentiment, all of those variables have arrows pointing to them, and that makes them endogenous. But you'll also notice too that the deference variable and support variable, not only do they have arrows pointing towards them, but they also have arrows pointing away from them. And in this particular system right here, we could treat deference and support as possible or proposed mediators of effects of other variables within the model. So for instance, deference we might treat as deference and support might be regarded as proposed mediators of the effect of age on sentiment. So at this point, let's go ahead and open up Stata and go into the graphical user interface and draw out our model. So I'm going to open up Stata right here. The data has actually already been imported. So we can easily go into the diagrammer by going to statistics, go down to SEM, structural equation modeling, and click on model building and estimation. So when I click on that, an interface opens up. It looks like graphing paper almost, and I'll just kind of maximize this, and this is where I'm going to draw my model. So as you're looking at this, pay attention to these buttons on the left side of your screen. So you can see over here, let me see if I can highlight it over here, we've got various buttons that we can use in order to draw out our model. So as you're looking at this, the first button I want to just draw your attention to is this little rectangle right here. So if I click on that, I can use that to draw in my manifest or observed variables. You'll see that I have a little button right here for a circle or oval, which is used to draw latent variables. You'll see we have a button for drawing a direct effect in the model. So basically that's the proposed effect of one variable on another, that being a direct effect. And then we also have a double-headed arrow that it can be used to draw in a covariance between variables or perhaps between error terms. So what we have to do is we have to activate a button by pushing it, and then we can do whatever drawing, and then we can deselect that button by clicking on this little arrow right here. And that also affords us some other opportunities as we draw. So let's go ahead and start out by drawing out our basic model. So I'm going to select the rectangle button. I'm going to press that and draw out my model. So I'm just going to click right here, click right here. I'm just going to kind of generally configure these how I'm thinking about that model, kind of spatially, if you will. So now we have our two exogenous variables that I'm drawing in. I'm going to draw in my two mediator variables and then my outcome over here. So the nice thing is that you can ultimately move things around and clean things up. I'm just kind of providing a general representation right now of where I kind of see things fitting. Just note that right now you can kind of see the outline of rectangle is still indicating that that button is activated. So if I keep pressing buttons, pressing enter right here or clicking on using my mouse, you can see that it continues to draw things out. So to deselect this, I'm going to go back to this select button and press it, and I can get rid of these boxes too by just highlighting each one and pressing delete. Okay, so now at this point, what I'm going to do is go ahead and associate my variables with these boxes. So to do that, I'm going to click on a given box, and you'll see up here, it says variable. You can use the little drop down, or you can type it in, but I'm going to go ahead and use the drop down and just select my variable. So I'm going to go to each of these boxes here and select the variable associated with it. And there you go. So now we have all of our boxes associated with a given variable. And like I said, I can kind of move things around just by clicking on it. Right now, we're still under the select button, so I can select an object and kind of move it around as I want to. Now what I'm going to do is draw in the direct effects in the model by clicking on the single-headed arrow where it says Add Path. So now we just basically highlight one variable and drag to another variable. So we have age predicting deference right there. And you'll notice that by virtue of drawing that path in, an error term is created for deference. So we don't have to actually have to draw in the error term. It's going to fill in automatically. We'll draw from age to support, and we get an error term that automatically shows up as well. Then we're going to draw from deference down to support right there, then deference to sentiment and support to sentiment, and then from years to sentiment. Okay, so there's our basic model right there. And then the last thing that I want to do is I'm going to kind of deselect this and go and select add covariance, because I want to add a covariance between my two exogenous variables. So I'm going to draw up right here from years to age, and you get your double-headed arrow kind of showing up that way. Just so you know, a little FYI, I'm going to just delete this for a second. And let's say I draw down, so I'll select that covariance again, I draw down. You can see it's kind of oriented a little bit differently. So that's not how I tend to prefer things to look. So I'm going to go up from years to age, and you can see that that's now looking nicer. So now I'm going to deselect that button right there, and now I can click on, select any object, and I can move it around. I can straighten up the boxes and so forth. If I highlight a given path, you'll see at the very end, it's almost like a little bubble at the very end, but I can click on that and I can drag the path around, and however I want to, in order to make things look a little bit nicer. So that's sort of a general overview of the diagramming capabilities in our interface. Now, the next thing that we want to do is we want to run our analysis. So I can go up to the estimation tab right here and click on estimate right there. And you'll see that there are three estimation options. There's maximum likelihood with missing values, and asymptotic distribution free. And the difference between maximum likelihood and maximum likelihood with missing values really pertains to the treatment of missing data. So if I select maximum likelihood, we're still using the maximum likelihood estimator when we're estimating the parameters for a model. But if you happen to have cases that have missing data on any of your variables, then those cases will be list-wise deleted. So the default treatment of missing data or cases with missing data is to remove those cases from the analysis. If you select maximum likelihood with missing values, then that actually utilizes full information maximum likelihood, and oftentimes that translates into a larger sample size. You're not going to lose as much data as you would if you were using maximum likelihood. So that's just kind of a FYI right there. We're going to leave things set for maximum likelihood for this presentation, but just to kind of keep things pretty straightforward. Now, if I click the SE Robust tab, this is basically to select various options for standard errors. You'll see that we have the default standard errors that are given. We can select robust standard errors if we want. You can also see down here that we could actually select bootstrap standard errors if we wanted to do that. We're not going to do that in this particular demonstration, but it is possible, and you'll also see you have options for the number of replications and so forth. Under let me go back here and reset this back to default standard errors. If we go under reporting, you have the option. If we click on this button right here, in our main output, you can get standardized regression coefficients or standardized path coefficients. We're not going to do that right now, but that was just kind of to show you where you could get that information. So at this point, we're just going to stick with the very basics and click on OK. And when we do that, it takes a second to run, but now we have a set of coefficients that are appearing in our output. And so as you can see right here, because we've actually we have not requested standardized coefficients, these values are all going to be unstandardized path coefficients that you see right here. So all of these are unstandardized path coefficients. You'll see also that we have estimates of means and variances for the exogenous variables right here. And we also have estimates. These are the residual variances right here. And by the way, in the context of SEM, when we talk about residuals or whatever, we might also use the term disturbances. So we have estimates of the residual or disturbance variances that are shown. And then you can also see the numbers that are appearing in the boxes for those endogenous variables. Those are intercepts. Now, as you're thinking about the general model, keep in mind that we essentially have an equation associated with each endogenous variable. So as you're looking at this, just think about it this way, that we have deference right here, which is regressed onto age. So that's the path coefficient for that regression. Then for our second endogenous variable support right here, we have support regressed onto deference and age. So we have the path coefficients right here and here that represent those associations. And then a third equation where we have sentiment regressed onto deference. So there's a path coefficient, support, path coefficient, and also years, there's a path coefficient there. So you could think about this as being the full model as being comprised of three submodels where we're estimating the parameters for each of those. Just another thing that I'll highlight is that if you click on, let's say, a path coefficient or path right here, you'll see that to the right, there's a little section that shows up that says details. It's got the path coefficient as well as standard error, z-value, and p-values for testing that coefficient and so forth. You also have standardized coefficients that are shown below. If you click on, these exogenous variables, you get the means and so forth. And so I'm not going to go into all that right now. Most of the time I spend my time interpreting the results that are provided in the main output. But that's just kind of what the details are. It's just if you click on different aspects or different components within your model, that's going to give you some more detail. So I'm going to minimize this drawing right here. And now we're going to take a look at our output. So as we're looking at our output, the first thing to draw your attention to is at the very top, you'll see that you're given syntax. So basically the graphical interface has constructed, based on the path diagram that we've created, it's constructed the syntax for running the analysis. So it's kind of nice because you can also learn more about how to write syntax by just kind of studying the formulation that's given. So you'll notice right here that on the far left, it starts off basically with the SEM command right here. And then you have a description of different paths within the model. So inside the first parenthesis, we have age with an arrow. That's just a hyphen followed by a greater than sign, pointing at deference. So age is serving as a predictor of deference. Here in the next set of parentheses, we have age pointing to support. So there's our second direct effect that we have specified. Then we have years serving as a predictor of sentiment right there. Then we have deference predicting support right here. And then over here we have deference predicting sentiment. And you'll notice that it kind of goes on to the next line or wraps onto the next line. And so this little thing right here should not be, if I was actually typing in the syntax, I would not want that little sign showing up. Then we have support predicting sentiment. You'll notice that after we've specified the basic paths in the model, we have a comma followed by various options. Right now we have covariance. And then so in terms of the specification of the covariance between age and years, what's showing up is years asterisk age. So that is how that's the syntax for generating a covariance between two variables. Is basically variable 1 asterisk variable 2 right there. And then we also have this little no caps latent at the very end that's been generated. So when we scroll down a little bit further, you'll notice that we get our regression coefficients, standard errors, z values, and p values, and so forth. So just kind of looking at this, you'll notice that in this coefficient column, these are basically, at least in the main structural portion of the model, which I'll just kind of highlight right here, these are unstandardized partial regression coefficients, or if you want to think about them as unstandardized path coefficients, you can think about it that way. It's literally meaning the same thing. So you'll notice too that right here, this is referring to a constant associated with the deference variable. This is actually the intercept for that first equation. So this is the intercept, and then the path coefficient, the unstandardized path coefficient for age is this value right here. So you'll notice that slope is negative. It's a negative 0.081. And basically what that's indicating is that individuals who were older were predicted to score lower with respect to deference. You'll notice that over here we have the z value which is computed as a ratio of the coefficient to the standard error, and we have a p-value which is used to test the significance of that path. So because the p-value is less than the conventional 0.05, we'll decide to reject the null hypothesis that the regression slope is 0. So in other words, we're going to interpret that the effect of age as negative and statistically significant. Then when we look at the next portion of our model, you'll see that we are predicting the support endogenous variable. So first we were looking at deference, which was the endogenous variable. We had the first equation. Now we have the equation predicting support. And so we have deference as a predictor. We have age as a predictor. And then down here, this is our intercept again. So the intercept is, you could think about it as an adjusted mean on the endogenous variable. In the context of linear regression, the intercept is just basically the predicted value on a dependent variable when all of your predictors are equal to 0. So it's essentially a predicted value or on, in this case, on our endogenous variable under the assumption that the predictors are 0. That may or may not be substantively important or relevant. It just kind of depends on whether values of 0 are actually can be found within the range of values on your variables in your data set. So that's just something to kind of keep in mind. So if that's not really the case, then we might just treat these more as nuisance parameters. But as we're looking at the unstandardized regression coefficient for deference, you can see that it is negative, and the unstandardized regression coefficient for age, in terms of predicting support, that's positive. So in terms of whether these are significant, you can see that both of these coefficients we would determine as being, or judge as being, statistically significant. That negative coefficient for deference is basically can be interpreted as indicating that individuals who scored higher on deference were predicted to score lower with respect to support for labor activism. So that's kind of the way to think about that. Whereas with the age variable, that positive coefficient is indicating that individuals who were older were predicted to score higher with respect to support for labor activism. Now, in terms of the third equation, where we have our endogenous variable sentiment, we have deference, support, and years predicting that variable. Again, here's our intercept for that third equation right there. And you'll see that the regression slope for sentiment or for deference is negative, and we have statistical significance for that. For support, right here, we see that there's a positive predictive relationship, and we have significance there. And then for years, we also have a positive regression slope, and we also have statistical significance for that. So as we think about the meaning of those coefficients, because that coefficient for deference is negative, that's basically telling us that individuals who scored higher on deference were predicted to score lower in terms of their level of positivity towards labor unions. Support and years, because those coefficients are positive, that's basically indicating that individuals who had greater support for labor activism and individuals who are older tended to score more favorably with respect to sentiment towards labor unions. Now, as we move down a little bit further in our output, you'll see that we have means for our exogenous variables. So these are the estimated means for those variables. You'll see down here that we have the estimated variances for our exogenous variables right here. The remaining variances that you see right here, these three, you'll notice that there's an E in front of these, E dot in front of these. And basically that's indicating that these are variance estimates associated with the disturbances for each of those endogenous variables. Then finally, if you go down to the very bottom, we have the covariance between age and years right here. So this is the covariance that's estimated, and we also have a test that allows us to test whether that covariance is statistically significant. And as you can see, the covariance is positive, and we have statistical significance. So basically, we're going to infer that there's a positive association between years and age in the population. Now, one thing that folks oftentimes will want to obtain is R-squared values associated with each of those structural equations. So basically the R-squared values that we would have associated with each of our endogenous variables. So one way that we can do this in Stata, we can use the drop down here. If we go to statistics and then scroll to the very bottom, you'll have a little option for post estimation. We could click on that and then select specification, diagnostic, and goodness of fit analysis, and we can select the equation level goodness of fit. So if I click on this and then click on OK, I end up with the R-squared values associated with my three endogenous variables. So, kind of keep in mind that the way Stata is set up is a lot of times there are basically the main analyses that can be carried out using drop downs or whatever, or even syntax, but then there are post estimation commands to get additional information or perhaps some supplemental analyses. So what we've done is we ran the basic model using the SEM command and really through the SEM builder interface. And now we've used a post estimation command in order to generate our R-squared values. You'll see over here, this is the actual post estimation command itself. And this is a good time to kind of note that you could basically, instead of going through the post estimation command, you could actually type it down in the command line here. So I'll type in estat EQGOF and hit enter, and you can see that I get the same information. So as you're looking at this, notice that we have the R-squared values associated with each of our endogenous variables. So there's deference right there. The R-squared value is 0.1095657. And keep in mind that there was only one predictor, which was the age variable. So we could say that age is accounting for about 10.9% of the variation and deference. For the second endogenous variable, we had support right here, and the R-square value is 0.243. So with respect to the support variable, we had two predictors. We had both age, and we also had the effect of deference. So age and deference were both predictors. So we could say that the joint effect of age and deference on support was about 0.243, meaning that those two variables jointly accounted for about 24% of the variation in support. Then we have the sentiment variable right here, and you can see that we have our R-square value that's given as 0.42, roughly 0.421. And in this case, for this particular equation, we had sentiment, we had support, and we also had years as predictors of the sentiment variable. So the joint effect of those three variables was about 0.421, meaning that those variables jointly accounted for about 42% of the variation in sentiment. Now, thus far, what we've been focusing our attention on is aspects, elements of local fit within our model. So you can think about our model as, kind of a superordinate kind of model, a global model. And then we have components within the model. And so we could think in terms of fit at the local level or the equation level, and also fit at the global level. So thus far, we've been focusing in at the equation level, but it's often times, generally speaking, when people are performing SEM, they generally are going to not only look at the global fit of a model, but also, the local level of fit for a model, but also look at the global fit. And so this is where fit indices come into play. So there are various fit indices that can be referenced in order to judge the overall fit of a model. So to obtain those fit indices, we can still go through the post-estimation menu if we want to, and I'll show you the code for that shortly. But we'll click on post-estimation and click on specification, diagnostic, and goodness of fit analysis, and we'll click on overall goodness of fit. And when I click on that, you'll see that we have this little drop down here, and we can select what statistics we want displayed. And my general preference is to go ahead and select all of the above. So we have it set for all. So then we'll click on OK, and you'll see that now we have a table that contains our goodness of fit indices. The code to generate this is estat space GOF, comma, and then stats parenthesis all. So if I go down to the command line, I can generate that very easily just by typing in estat GOF, comma, stats all, and in parenthesis there, and hit enter, and there you go. Now, in terms of the fit measures, the first one that you see in the output is the chi-square goodness of fit test. So let me just kind of clean that up just a second there. And as you're looking at this, you can see that right here it says chi-square. There's a degrees of freedom in the parenthesis, and then there's a p-value that's given. So this right here, this is the chi-square value that's computed, and then we have a p-value that's given right here. So the chi-square goodness of fit test is kind of the first fit measure on the scene, so to speak, to evaluate the overall fit of a model. And the basic logic is that what we're doing is we're making a comparison between the observed sample covariance matrix and and an estimated covariance matrix that's implied from our model, or the pattern of associations that we specified. So what we're looking for, or looking at, is the degree of discrepancy between the sample covariance matrix and the model implied covariance matrix. So the more discrepancy there is, the less fit that we have in terms of our overall model. So the chi-square test is a test of the discrepancy between our model implied and sample covariance matrix. And you could think about this test as essentially a badness of fit test, because discrepancy represents difference, and difference is an indication of lack of fit. So with respect to the chi-square goodness of fit test, if that test is statistically significant, then that's regarded as an indication of poor fit, because you don't actually you have a discrepancy between the sample covariance matrix and the model implied covariance matrix. If you have non-significant test result, as we do right here, it's 0.3, the p-value is 0.305, then that's indicating that we have overlap or substantial overlap between the sample covariance matrix and the model implied covariance matrix. And so that's actually an indication of good model fit. Now, keep in mind, though, that the chi-square goodness of fit test nowadays is largely regarded as, still a lens that you can look at fit, but folks pretty much understand now that this test oftentimes can be overpowered as a result of the sample sizes that are typically used in the context of when you're carrying out structural equation modeling. In general, SEM is a large sample technique. So we're assuming larger samples, and so with larger samples comes greater power for rejecting a null hypothesis. The null hypothesis for that chi-square test would be an exact fit between the sample and model implied covariance matrices. Well, when we have very large samples in the context of SEM, it's a lot easier to reject that null hypothesis and conclude that there's a significant discrepancy. So for that reason, you'll oftentimes see, even if there's modest misspecification of your model, you can still end up with significant chi-square goodness of fit tests, and which would signal that there's a lack of fit. So for that reason, a lot of times, it's generally recommended to consult other fit measures and still report on the chi-square test, but also look at other fit measures to kind of round out your perspective in terms of the model fit. So other fit measures that are reported in our Stata output include, down here, we've got the RMSEA. That's the root mean square error of approximation. And this is the value that's printed out right here. So there are various rules of thumb out there that float around out there in terms of what constitutes a good fitting model and so forth. So I'm going to stick with, for this one and the others that I talk about, I'm going to stick with the conventions that are laid out in that Whitaker and Schumacher book, because they're pretty much on par with most recommendations. So as we're thinking about this then, with the RMSEA, the basic idea is that if I have a value that falls, let's say, between 0, which is the lower bound for the RMSEA, and around 0.05, that would be evidence of a close fitting model to the data. So that would be regarded as close fit right there. So even if there is some misspecification and some discrepancy, within that range right there, that would signal a close fit to the data. Then RMSEA values from about 0.05 up to about 0.08 would be regarded as acceptable fit. Now, and then, values that fall between, say, about 0.08 and 0.10 might be considered an indication of mediocre fit. And then values that would fall above 0.10 would be considered, poor fit. So if we use this kind of system right here, or these conventions for judging the fit of our model, you can see our RMSEA is about 0.035. So that's going to lead us to conclude that we have evidence of a close fit of our model to the data. Another index that we'll refer to then, and kind of similar to the RMSEA, but is the standardized root mean square residual. So in this particular case right here, the SRMR, it also has some conventions for judging the fit of a model. So basically, a value of 0 would signal perfect fit, if you will. And then values that fall that are basically 0.05 or less, I'll just say less than or equal to 0.05. That would be an indication of good fit of the model to the data. So we'll just say good fit right here. And then values that fall between 0.05 and 0.10 might still be regarded as acceptable fit. Okay, so using these conventions right here, you can see that our standardized root mean square residual is 0.037, which would be consistent with a good fitting model. The next two indices that we're going to refer to are the comparative fit index, or CFI, and the Tucker-Lewis index, or the TLI. And so the basic idea behind these fit indices is kind of comparing your model against a null model, where essentially the null model would be one where there's no relationships among any of your variables. So the theoretical range for these indices is generally between 0 and 1, although you can still have values that might fall outside of that range, a little bit outside. But in terms of making judgments about fit, the conventions for these indices are generally 0.90 or greater would be an indication of an acceptable to good fitting model. Ideally, we would be looking for values that would be equal to or greater than 0.95. So, values that might fall in this area right here would be considered really more indicators of more superior fit, although values of 0.90 or greater are generally regarded as good to acceptable fit. So with that in mind, then, as we look at the indices that are showing up over here, the 0.996 for CFI and 0.988 for TLI, you can see that we have evidence of, evidence of a good fitting model, and really a quite good fitting model.